So continuing on with section 12.1, this is on ellipses. So now we're talking about ellipses whose center is away from the origin. So those are certainly more complicated than the ones whose center is at the origin. So let's look at this equation of an ellipse. First of all, we know it's an ellipse because we have both variables squared, and we've got this kind of, form that over A over B business here. Now remember, if there's nothing written, that's an understood one right there. So a few things that we can already tell from looking at this. We can tell right here that we know in an ellipse that this larger denominator is my A. So I can already tell, it's A squared. I can already tell what A is going to be because we know A squared is 16, so we can already tell that A is going to be 4. This is going to be my B squared, so B is 1. Because this larger number is under the X, I can tell that I'm going to have a horizontal major axis. That means that my ellipse is going to be looking like this instead of, kind of going up and down. I can also tell the center from looking at this. Now, remember the center, the formula, the standard form of it has a subtraction symbol. So these I need to look at in terms of subtraction. So instead of writing x plus 2, let me write it as x minus negative 2 squared over 16, which actually, you can write as, if you want it to be a nice little standard form here, plus y minus 3 squared over 1 squared equals 1. Now I can already tell what that center is going to be because the center is this number that's being subtracted from x and this number that's being subtracted from y. So pulling those together, I get that I have a center of negative 2 comma 3. I know it's really tempting to want to say that it's going to be positive 2 minus 3, but remember that the standard form has a subtraction in it. So it's this number after the subtraction that is your h, and this number after the subtraction that's your k. So remember, that's hk on your formula sheet. So just like that, I've got my center. I know which direction the ellipse is going. I have A and I have B, so now I can go ahead and find C because I have that relationship as well, that A squared minus B squared is C squared. So I wrote that up a lot better over here. So I've got the center, the major axis. I have A, I have B. I know the relationship between A, B, and C. Don't get that confused with the Pythagorean theorem. It kind of is the Pythagorean theorem, but C isn't your hypotenuse for this one. So plugging in A squared and B squared, I get that C is the square root of 15, or about 3.87. If you want to use the square root of the square root of 15, you certainly can. If you want to use the decimal, you can. I hope that I have, everything set up to where WebAssign will accept that. Fingers crossed. There's a tolerance setting in there that I checked and said, hey, be more tolerant of, different answers. So we'll see if that helps. Okay, so now if we want to find the foci and the vertices, we're going to use So since we have that horizontal major axis, okay, let me flip back here a little bit, that horizontal major axis, the foci have this form, the vertices have this form. Now rather than putting these on the formula sheet, for me it just kind of makes sense that, hey, if it's horizontal, then it's the x value that's changing. Right? The foci are moving along the x-axis, away from the center. The vertices, same thing. So they're all along that horizontal major axis. So taking my h value of negative 2 plus or minus root 15 comma k, I get that. If you want to graph it, you probably need the decimal version. So I have those two. That is negative 2 plus root 15, and that's negative 2 minus root 15. So those are my foci. So you can see those graphed out there on this sad little ellipse that looks more like a football that's been run over a few times. The vertices uses A, whereas the foci use C. So if I take H from my center and do plus or minus the A value, which was 4, -2 plus 4 is 2, -2 minus 4 is -6. So I get those 2 points for my 2 vertices. And then how did I get these points up here? Remember, I needed these points up here to tell me like how wide or how skinny the ellipse is going to be. Well, those come from the B value. The B value is going to tell you about the minor axis. So a B value of 1, just from the center, boop, I went up 1 and down 1, and those told me how flat or how fat my ellipse is going to be. Okay, example 5. This one's going to be a little more complicated because it's not given in standard form. So we're going to have to do some work to start with to get this into standard form. We're going to have to do a lot of completing the square. So first I'm going to group my x's together and then my y's together, and then I'm going to complete the square for both. So here's the work for that. So you can see I grouped my x squared and my 6x together, and then I left a space to complete the square. Then I have the y squared, and actually, you know what, I kind of skipped a step in there, so you might want to see the behind the scenes here. So let me go back and do this for you. So I had the x squared plus 6x, and then a space. Then I had my 9y squared minus 18y, space, equals -9. This one's already set up to complete the square. In order to complete the square, you have to have a coefficient of 1 on your squared term. This one's set to go. This one's not so much. So I have to factor out that 9 first, just from these two terms. So I'll have x squared plus 6x. Then I'll factor out that 9 and get 9 squared minus 2y equals -9. Now this is ready to complete the square, and that stuff's ready for me to complete the square. Now you may remember completing the square from like college algebra or from other courses, but to complete the square, it means we're going to find a number that we're going to put right here so that this trinomial factors into the same thing twice, or that thing squared. So we're wanting to find a number so that this factors into some quantity squared. Now we want that because, you know, ellipses have that form of like some stuff squared, some other stuff squared. So that's what we're going after. This is not a guess and check game here. There is a systematic way of finding that magic number over here. So we're going to take half of that middle number. Now I say middle because I'm about to add a third number here. So half of that number, and then square it. So half of 6 is 3. 3 squared is 9. So boop, I'm going to add 9. Now, because I'm adding 9, my equation has now changed. To keep this thing equal, since I added 9 right here, I'm going to have to go over here and add 9 to balance it out. All right, so now I'm going to do the same thing for the y's. I'm going to take half of that middle number there, and I'm going to square it. Now you might notice that I ignored the negative here. That's because I know I'm always going to square it, so the negative doesn't even really matter. So half of 2 is 1, and 1 squared is 1, so plus 1. Now you might think, oh, I'm going to go over here and add 1. I'm not. I'm going to go over here, and I'm going to add 9. What? Why didn't you just add 9? Because this 1 right here is being multiplied by that 9. So I have to take that into consideration. the fact that that 1 is inside those parentheses that's being multiplied by that 9. So now I've got both of these squares completed. This first set of parentheses will factor into x plus 3 times x plus 3, or x plus 3 quantity squared, right? Because I completed the square. Plus 9, this one will factor into y minus 1, or y minus 1 quantity squared. Over here, all that adds up to be 9, because that was a minus 9 plus 9, so that's just 0. Right, so that was a lot of the behind the scenes stuff that all went down right here. So now here's what I've got. I've got this x plus 3 quantity squared plus 9 times y minus 1 quantity squared equals 9. Very much looking like an ellipse. But the main thing an ellipse has is a 1 over here. So I need that to be a 1. Well, I'm going to divide everything by 9 to make that be a 1 over here. So once I do that, dividing this by 9, why did this one become a 1? Well, because when I divided that term by 9, those 9's canceled out. So that just left me with a 1. Boom, there's my standard form. So now I want to find the center, the foci, and the vertices. All right, so we can just read off the center. So it's going to be -3, comma, +1. Now you can either think of it as, okay, I know that the standard form of an ellipse has this x minus h form to it, or some students tell me that they just remember to use the opposite. You know, they'll say, well, I just remember that that's going to be a -3 and that's going to be a +1. Whichever way you go about it, it's fine with me. So here's what we got so far. We got a center at -3, 1. This bigger denominator is under the x, which means we have a horizontal major axis. Also tells me that a squared is 9, so a is 3. B squared is 1, so b is 1. I have that relationship between a, b, and c that I can then use to find that c is 2√2, or square root of 8. And I'm going to need c to find those vertices. Or sorry, the foci. Sorry, not the vertices, the foci. I need a for the vertices. So we have the center. Then we had that a value of 3 from the previous page. So my vertices are going to come from h plus or minus a, comma k. So doing those computations, -3 plus 3, -3 minus 3. And then the foci come from using c along with the center. This is a lot messier, right? Because we have that 2√2 business. So I just split this thing up into its 2 pieces. If I were going to graph it, I would probably change these to decimals. Well, I would. I'd change them to decimals if I was going to graph this. But because I'm not graphing it, I'm just going to leave them as roots, because why bother? Okay. All right. Last one, and it's a good one. It's a word problem. So a semi-elliptical archway, or a semi-elliptic archway, has a height of 20 feet and a width of 50 feet. Can a truck 14 feet high and 10 feet wide drive under the archway without going into the other lane? This is not a yes or no question based on your opinion. This is a mathematical question. So I need justification for this. Now, first of all, what does semi-elliptic mean? Well, semi meaning half, so it's half of an ellipse. All right, so we have this kind of half of an ellipse thing going on here. So we have that, and we got the road, and we've got the middle of the road, right? So we've got this lane, and we have this lane. So if I kind of look at this on an XY coordinate plane here, you know what, let's look at it on an XY plane to where this is going up and down. Don't look at this as like the road going forward. Let's look at this going up and down. That way we can talk about this being the height, that being the width of it. So it has a height of 20 feet, and it has a width of 50 feet, but that doesn't mean this number out here is going to be 50. This is going to be 25, and that's going to be negative 25. Because the full length of it is 50. So can a truck 14 feet high and 10 feet wide drive under this without having to go into the other lane? Well, let's just, say right here would be going into the other lane. So can a truck that's 14 feet high, so I don't know, somewhere around in here, and 10 feet wide, this is not drawn to scale, so don't even pretend like it is. Can that fit? Well, let's do it this way. Because we can't just guess. So instead, what we're going to have to do is say, okay, let's say that one tire is going to be riding on that line. And let's say that's 10. So the question becomes, what is that height right there? So if that truck is 10 feet wide and it's got to go under it, if this point right here is bigger than 14, we got some room. If this number is smaller than 14, we don't have any room. Now if it's exactly 14, now you're getting wedged in there. But all right, so that's kind of the setup. That's where we're going with this. Now notice how I made this all nice and symmetric. So because of the symmetry that I did here of saying that, this is 25, this is negative 25, that puts the center of my little half ellipse at the origin. And we know from experience now that when it comes to ellipses, the ones at the origin are much nicer to have to do computations with. Okay, so let's go back over here to the prettier drawings. All right, so we've got that. Oh, you know what? I took the approach of doing this where that was 14, and then I went looking for that. Whereas I originally drew it out and said, hey, that's 10, what is that? It really doesn't matter which way you go about it. It just so happens that when I wrote these up, I chose to do what is this width that goes along with 14. I could have gone, what is the height that goes with 10? And I'll show you how that's going to play out, that you could have gone either direction here. I just obviously didn't look far enough ahead here when I started writing all my other stuff down. Okay, so we've got the center is at 0, 0. I can tell there's a horizontal major axis because this is 50 units long, right? And that minor axis would only be 40 if I, kind of continued that elliptical shape. These points out here are my vertices. Those are the ends of the major axis. This, my minor axis, I can tell has a length of 20, or sorry, that half of the minor axis there, that B value has a length of 20. Now I don't need C, I don't need to know where the foci are, but instead I need A and B just to give me the equation. So that x squared over a squared, y squared over b squared equals 1. I don't need h and k because my center is 0, 0. So once you get this equation, you can plug in a and b, a coming from that half the length of the major axis and b coming from half the length of the minor axis. So I get this form right here. Now I chose to say, hey, when the height is 14, what is that width going to be? For this one that I drew out first, if I had that x squared over 625 plus y squared over 400 equals 1, I could have said, okay, when x equals 10, what is y? So you could do that, or when y equals 14, what is x? So you could go either way. So since I chose, 14 on this one, let's go with that. So that'll be 14 squared, which is 196. Now I just have to solve this equation for x. I realize that this looks really menacing, but it really isn't. I'm just going to subtract 196 over 400 from both sides of this equation, undo that division by multiplying by 625, and then take the square root. So if I take 1 minus 196 over 400, I get 51 over 100. I multiplied both sides by 625. Now, I did all of this and just kind of left the fractions as I went along. You certainly don't have to if you don't want to. I just chose to leave the fractions in there along the way. And then, of course, that ends up being plus or minus the square root. But because I'm looking in this kind of right lane over here, I just went with a positive one. So I got about 17.85. So what does that tell us? That tells me that at a height of 14, that width here is 17.85. So a 10-foot truck is going to be over here and have more than 14 feet clearance. So it will fit. Does that make sense? So because this width right here at a height of 14, that is 17.85 feet away from the other lane. So the 10-foot wide truck has room because the way this thing is shaped, this 14 is the low point over here and all this is above 14. So we know that that 10-foot truck can fit into this 17-foot space and easily clear that 14 feet up there. I know this is kind of messy, but it's, a pretty cool application of ellipses. There's a lot more cooler ones out there than these, but this is a common one that shows up is that. So, okay, so at long last, that concludes section 12.1.